I'm working with a dataset containing information on individuals. This data includes both numerical and categorical features. Think of it like a spreadsheet. This dataset has numbers representing age and income. I'll use these for my machine learning model. These are continuous values. I also have categorical features which represent different categories, such as gender and city. These aren't numbers, they are labels. I need to transform these before I can use them in my model. This is a tool I use to scale my numerical features. It transforms the numbers to have a mean of 0 and a standard deviation of 1. It helps to avoid features with larger values dominating the model. It's like standardizing a test score. I'll use this to turn my categorical features into numerical representations. This involves creating binary columns, 0 or 1, for each category. For example, male and female will become two separate columns. It's a way to make the categories machine readable. This is a powerful scikit-learn tool. It lets me apply different transformations, like standard scalar and one-hot encoder, to different columns of my data simultaneously. It's like a Swiss Army knife for data cleaning. After I use the column transformer, I will have clean, pre-processed data ready for building my machine learning model. Ready to train my model. I want to create a machine learning pipeline. This involves using the Compose module in the scikit-learn library. It's a convenient way to handle data pre-processing and modeling steps. It's a crucial step for model building. I see this option uses column names, age, and income for numerical scaling using standardscaler, and gender and city for categorical encoding using onehotencoder. It's super clear and easy to read. Here, I'm using column indices instead of names. 0 and 1 represent the first two columns, numerical, 2 and 3 are the next two, categorical. Remainder equals pass-through. Means any extra columns are kept untouched. It's functional, but names are usually easier to understand. This uses slices to select columns. Slice 0, 2, selects columns 0 and 1. Numerical, and slice 2, none, grabs columns from 2 to the end, categorical. It's concise but might be less readable than using names. This option is similar to A, but it also drops a column named unnecessary column. This is a powerful addition, allowing you to handle unwanted features during pre-processing. It's super handy. I'm working with a dataset containing information about individuals. This data includes numerical values like AGE and INCOME, and categorical values like GENDER and CITY. These are the columns in my dataset that contain numbers, specifically AGE and INCOME. I'll use a technique called standardscaler to adjust these numbers, making sure they're on a similar scale. These columns hold values that represent categories, like GENDER, male, female, etc., and CITY, New York, London, etc. To use these in my machine learning model, I need to convert them into numbers. I'll achieve this using a process called onehotencoder. This is a powerful tool from the scikit-learn library. It lets me apply different data transformation steps to different columns in my dataset simultaneously. Think of it like having multiple specialized workers each responsible for a specific part of the data preparation. It's crucial for handling datasets that have a mix of numerical and categorical data. This is a pre-processing step that centers data around a mean of 0 and scales it to unit variance. It's very useful to put numerical features on a similar scale before feeding them into a machine learning model. This ensures that features with larger values don't disproportionately influence the model. This technique converts categorical features into a numerical representation. Instead of having male and female, it creates new columns representing each category, like gender_male, gender_female, with a 1 indicating presence and a 0 indicating absence. This is essential for most machine learning algorithms to handle categorical data. Here, I'm using the columntransformer to create a pipeline. Applies the standardscaler to the AGE and INCOME columns, by name. Similarly, applies the ONEHOTENCODER to the GENDER and CITY columns, by name. This is similar to option A but uses column indices instead of names. Refers to the first two columns, 0 and 1, and refers to the last two. Ensures that any other columns are left unchanged. In this option, I'm using slices to specify columns. Selects columns from index 0 up to, but not including, 2, which are my numerical columns. Selects from index 2 to the end, which are my categorical columns. This option shows how to drop unnecessary columns. Explicitly removes a column named unnecessary _ column. This is quite useful for cleaning up datasets before preprocessing. I'm building a machine learning pipeline using the Sklearn library. Specifically, I'm focusing on its compose module, which provides tools for preprocessing data. This involves preparing my data before feeding it to a machine learning model. I have a dataset with different kinds of features. Some features, like age and income, are numerical. They are numbers. Others, like gender and city, are categorical. They represent categories or groups. I'm using a column transformer to handle these different feature types in a single step. It applies different preprocessing steps to different columns. The column transformer uses transformers to apply the different preprocessing steps. One way to specify which transformer applies to which column is by using the column's name. I find this way easy to read. I can also use the column's numerical index, its position in the dataset, starting from 0, to specify which transformer should apply. This approach is less readable when you have many columns. I can select a range of columns using Python's _slice object. This is useful for selecting consecutive columns. If I have a column I don't need, I can explicitly drop it using the drop transformer. The output is a preprocessed dataset that's ready for a machine learning model. I use standard scalar to transform my numerical features. It scales them to have 0 mean and unit variance. To handle categorical features, I use one-hot encoder . It converts categorical values into numerical representations using one-hot encoding. This is a second reference to one-hot encoder in the context. The word drop indicates I am going to remove a column from my dataset using column transformer. I'm presenting you with a machine learning problem. We're building a pipeline using Sklearn's compose module. We have data with numerical features, like age and income, and categorical features, like gender and city. I need you to figure out the best way to preprocess this data using standard scalar for numerical features and one-hot encoder for categorical ones. Which column transformer configurations do that correctly? Let's see how well you understand column transformer This option uses slices to select columns. Slice 0, 2 selects the first two columns, 0 and 1. For numerical scaling, and slice 2, none, selects from the third column onwards for one-hot encoding. I like how concise this is. This option showcases how to drop unnecessary columns using drop unnecessary _ column, It also correctly scales numerical features and one-hot encodes categorical features. Pretty neat, right? It shows that you can drop specific columns too. This uses column names to specify the transformations. It's clear and straightforward. I can easily see which transformer is applied to which columns. Excellent readability. This is the core problem. I am asking you to identify which column transformer configurations correctly preprocess the data. Remember, column transformer lets us apply different transformations to different parts of the dataset simultaneously. This is the Sklearn class we're using to apply different transformations to different columns of a dataset simultaneously. This is the key to solving the problem. This is the overall topic of the question. How to configure a column transformer in Sklearn. We are using this to process our data effectively. Our dataset has age, income, gender, and city columns. This is our raw material for the machine learning pipeline. A categorical feature representing gender. We'll need to one-hot encode this to make it usable for machine learning. Another categorical feature representing the city. Same as gender, we need to one-hot encode this. A numerical feature representing the age. We will scale this to improve model performance. A numerical feature representing the income. We will scale this too. This option uses column indices instead of names. Backquote 0, 1, backquote selects the first two columns for numerical scaling, and backquote 2, 3, backquote selects the next two for categorical encoding. Backquote remainder equals pass-through, backquote keeps any extra columns. This works but may be less readable for larger datasets. I'm dealing with a dataset containing both numerical and categorical features. Specifically, AGE and INCOME are numerical, while GENDER and CITY are categorical. This is typical in many machine learning problems. These are the features I will scale using STANDARDSCALER to ensure they have a similar range of values and to avoid features with larger values dominating the model. I will convert these features into numerical representations using one-hot encoding via ONEHOTENCODER. This technique creates new binary columns, 0 or 1, for each unique category. I'm using the actual column names, AGE, INCOME, GENDER, and CITY, to specify which columns get which transformation. It's easy to read and understand. This line defines a COLUMNTRANSFORMER object called CT. TRANSFORMERS is a list of tuples. Each tuple specifies a name, NUM for numerical, CAT for categorical. The transformer to apply: STANDARDSCALER or ONEHOTENCODER, and the columns to which it's applied. Instead of names, I'm using numerical column indices: 0, 1, 2, 3. This is efficient but can be less readable, especially with many columns. Tells it to leave any extra columns unchanged. Similar to the previous example, this defines a COLUMNTRANSFORMER, but uses column indices. I'm using SLICE objects. Selects columns 0 and 1, numerical, while selects columns from 2 to the end, categorical. It's concise for selecting ranges. Same as above but utilizing column slices. Here, I explicitly drop a column named UNNECESSARYCOLUMN using. This is useful for handling unwanted columns in your data. Similar to before, but now it includes a step to drop a column that isn't needed for analysis. This is the final dataset after I've applied all the transformations, scaling numerical features and one-hot encoding categorical features. It's ready for modeling. I use column transformer to apply different transformations to different subsets of my data. Think of it as a way to manage and organize multiple pre-processing steps simultaneously. It's a crucial tool for building efficient machine learning pipelines. I use standard scaler to standardize my numerical features. This involves centering the data around a mean of 0 and scaling it to a standard deviation of 1. It ensures that all numerical features have similar scales. This prevents features with larger values from disproportionately affecting my model. I use one-hot encoder to convert categorical features, like gender or city, into a numerical representation that my model can understand. This involves creating new binary features, 0 or 1, for each unique category. This method avoids imposing any unwarranted order on my categorical features. I directly specify the columns by their names, such as age and income. This approach is highly readable and easy to maintain. Instead of names, I use numerical indices, 0, 1, 2, etc., to refer to my columns. This is less readable but works when column names aren't readily available or are cumbersome. I use slices like to select contiguous ranges of columns. This is a compact way to select multiple columns. For example, selects columns with indices 0 and 1. I can explicitly drop irrelevant columns using the drop option. This is useful for cleaning up data before modeling. For example, I might remove a feature that is completely unrelated or is considered noisy.